Okay, so good morning, everyone, and welcome to this new session of the seminars. Today we have someone from the ISC, which you probably already know, Javier Licandro, and he will be talking to us about the latest addition to the Atlas network, who was just recently built, this robotics telescope, and what can we do with it, I guess. So whenever you're ready, the floor is yours.
Okay, thank you. Can you hear me well? Now see if I have to move the mics. First of all, thank you for coming. For me, it's a special date. It's a day of somehow a celebration date after a few years of hard work with the Atlas team to make this instrument come into reality. Here you have a nice picture by Juan Carlos Casado of the installation at night. I will start summarizing what Atlas is. Atlas Teide is a robotic telescopic installation built by the IAC. It's an IAC telescope. It's in fact I think it's the third telescope, the second optic telescope built by the IAC at the Teide Observatory. And it is the first that it is fully robotic. Atlas Teide is included in the strategic plan of the Canary Island Observatory 21-24. And it is a reality thanks to the funding by the European Union, Next Generation, EU, those famous PRTR projects, funded by two projects, right? With NIAS-PI, called Telescopio Atlas and el Observatorio del Teide, to build common service and investigation, scientific equipment. And the other is one of the actions of the last ICTS 2022 implementación de actuaciones para la mejora del LOCAN by the IAC, and Atlas is one of the actions funded. And Atlas Teide is not only a telescopic installation. It's also part of a network called Atlas that it is operated by the University of Hawaii, the IFA, and there is an agreement signed with the University of Hawaii to operate and explore the science produced by this Atlas. As part of this Atlas network, I will explain what it is in a moment. And for the Spanish community, the important thing is that this Atlas unit allows all the community, the whole Spanish community, to have access to the data products of the whole Atlas network, past, present, and future data of the Atlas network. And we have Here I can see a pair of colleagues that are using Atlas data for his own research. What is the Asteroid Terrestrial Impact Trust Alert System Atlas? It's a NASA-funded early warning impact alert system. Basically, it's a network of wide field small telescopes with the aim of discovering small nears close by the Earth and in impact trajectories as soon as possible, but to make the necessary prevention of the impact hazard. And also, of course, to produce science, right? The aim is not only the discovery, but to do photometry, astrometric measurements of moving objects, detection of cometary-like activity, detection of new comets, and as part of the science of Atlas, there is time domain astronomy. People of supernovae or gravitational waves, novas, etc., whatever you think that you need observations at least 1 point per night, up to magnitude 19.5 can be done. In fact, up to now, Atlas discovered more than 1,000 near asteroids, more than 100 of them potentially hazardous ones, more than 100 comets, and about 5,000 supernovae. How Atlas works? As I say, Atlas take wide field images. Here is a 30-second wide field image obtained with Atlas data almost 2 days ago. These images have thousands of objects there. And the way of dealing with new objects, the way that Atlas do is to subtract a wallpaper. What is the wallpaper? It's a master image of the whole sky created with their own observations of the Atlas telescopes, right? Atlas observed the whole sky every year, more or less, with the 5 telescope we have now. So we can create a very high signal-to-noise map of the whole sky. So if we subtract, it's not that simple, and need some processing to subtract this wallpaper from the images. What remains, part of noise, are the transient objects. Okay? Transient in the sense that can be moving object like ours, or can be object that simply change its brightness in the images. They appear very rapidly, they are detected and measured. And let me put an example of what they do with asteroids. With asteroids, we do that is the reason we do 4 images per night, separated by about 1 hour. Here you can see 4 images. This is obviously a small part of the image, obtained every 20 minutes, 30 seconds each. And once you subtract the wallpaper, an object remains. In this case, it's a very bright one, easy to see. And the software makes a detection of these objects, detects hundreds of objects per image. Images are very big. And then to look for an asteroid, what they do is to look for object that if you link the four images should follow a trajectory, an almost linear in an hour is a linear trajectory in the sky, moving in the sky. That's the case. You can see here the motion in right ascension and declination of this target. Here you can see the images again of the asteroid, of this near asteroid moving between the stars. Right? What Atlas do is detect all the moving objects, measure the position and the brightness, and report to the Minor Planet Center every night. This can be used for a lot of different aspects of asteroid science. And in the case of the objects that do not move, like supernovae, there is a group in the UK, also part of the Atlas team, that that detect the objects in the images and also report the brightness of and position of the targets. And as I say, as we repeat the sky several times per week, we can follow up and create light curves or whatever you want from this kind of objects. Actually, to the fourth telescope that Atlas had, the first one in 2015 installed in Haleakala, the second one in 2017 in Mauna Loa. Then in 2022, when we started to think in Atlas Teide, to start to make the designs of Atlas Teide, the two Southern Atlas telescope, one in Chile and the other one in South Africa, were installed. And finally, in January this year, Atlas Teide was installed in our observatory. What can be done with a network of telescope like this? You can observe something like this every night. You have a distribution here of the 5 different telescopes, what they observed the night of September 30, right? And you can see that we were able to map most of the visible night sky this day, right? And we can do it every day. The only constraints for us is the moon. We cannot observe very close to the moon because also of obvious reason are on the horizon of our telescopes. Another advantage of Atlas is that no other survey, planetary defense survey do, is that we observe in the galactic plane. The method, the subtraction method is very nice. They do a very good job to detect objects in the galactic plane, even in a very crowded fields. Of course, not with the same signal to noise. We don't go as deep, but we are the only survey that does this kind of discoveries. I will show you later one of the objects that was discovered in the galactic plane. This is the near asteroid discovery rate by surveys. Atlas started in 2015, and it's the light gray, the light blue part of the histograms. Notice that we have two very big surveys. One is Pan-STARRS, the other one is Catalina, with much bigger telescope that detect much finer objects. But the difference with Catalina and Pan-STARRS is that Catalina and Pan-STARRS map a small region of the sky. To come back to the same region, it takes several days, while Atlas is capable of observing the whole sky. And that is very important in the case of planetary defense, in particular to detect small virtual impactors, because the brightness of an object increases a lot when passing close to the Earth. And when they are coming close to the Earth, the Earth distance varies very rapidly. And an object that the day before was magnitude 21 or 22 can be 18 the following night. So if you are mapping the whole sky, Atlas will detect this object, and probably the object in a few hours, on a few days, if it is if it is an impactor, will impact the Earth. So if we are looking outside the region where it is, we will not see it even with a larger telescope, like Pan-STARRS and Catalina. Notice some things here that are very important. That is why Atlas Teide is so important. If you go to these parts, only the gray parts are not American surveys, right? And you can notice that there are three surveys that do most of the discoveries. To be part of a survey like Atlas is very important. Why I was so interested in this, I will explain in a minute. Also, you probably heard about Atlas because of two objects that were recently discovered. One was the Big Bang Impactor 2024 NY4, discovered in December, the one that gonna impact the Earth. So sorry, we will all die, etc., etc. The press every day coming to what is the probability? Oh, now it's increasing by a factor of 0.1. Oh, crazy. We have been working with this object and was discovered with one of the Atlas telescope, the one in Chile. Fortunately, will not hit us in 2032. But if you plan to go to the moon and buy a resort or whatever there, take care because it still can impact the moon. The other amazing object recently discovered by Atlas is the interstellar comet, 3Y Atlas. And, you know, all the interest and importance of the discovery of an interstellar comet. This is we only know 3 of such objects. And the important thing is that when discovered, 3Y Atlas was moving in the galactic plane. No way to discover it without Atlas. So let's go to the history. By 2019, I had the idea of having a discovery program of NEOS at Teide. Why? Because we have a long tradition since Julia de Leon thesis till now. We have a long tradition in near asteroid research for planetary defense and for the understanding of the solar system, right? Our observatories are the European reference observatories in planetary defense in all the aspects related to the follow-up, photometry, spectroscopy, physical characterization of near asteroids. Not only our group, other European groups use the NOD, the TNG, and actually we are using a lot the new TTT telescopes in Teide to do physical studies of near asteroids. But we lack one of the feats of this the research, that this is the discovery of new asteroids. I like that it is also fought by European fault. We don't have programs. I mean, in fact, there is a long program in preparation that is taking 20 years and still it's not working. So the idea is, okay, why not having an Atlas telescope here? And I started to talk with John Tonry in some meetings, trying to convince them that, okay, you are going to put one in Chile or another in South Africa. Why not the next one in the Canary Islands? And then the pandemic comes. And with the pandemic, the PRTR fundings. An opportunity appeared to us for funds to build a telescopic installation. And I talked to the former director, Rafa Rebolo, and we decided to go for this. We put Atlas in the strategic plan of the Canary Island Observatories and asked for a project to the call of Proyecto de Equipamiento Científico Tecnológico para un Servicio Común de Investigación 2021. We got the money, surprisingly, finally. We got something about 40,000 euros for building the Atlas unit. So we started rapidly to contact again John and Larry at the Hawaiians people that drive Atlas, and started to contact the builders, the companies that built the Atlas telescopes. And we rapidly noticed that it will be impossible to build another unit as the others. So we went for a new design, and we decided to go for a different kind of design. We went for a telescope array of an array of small telescopes using commercial off-the-shelf materials, So nothing is built specifically for the person. We can buy the components and make an instrument that at the end do more or less the same that the other atlas does. Where we made in early 2022, we finished this design. There is a drawing here. I will explain a little bit more what it is all this. And we built a prototype at the Teide Observatory in 2023. Why we need for this new atlas design? Well, basically because when we went to the company that built the Wright-Smith optical telescope assembly, they say, oh, we are in the middle of the pandemic. The cost increased a lot, and it will take no less than, let's say, 3 years to build only the optics, not only the optical tube. So no way, we have no funds to complete the telescope, and it was completely out of the time line we have. So we looked for the alternative, and this is the design we agree with John Tonry. Basically, we planned to go for a modular structure. We want a telescope array. We can build something that put all the small telescope together and moving and so on. But if you do in a modular way, you can build you can build 1, 2, 3, 4 modules or whatever you want, or whatever the money you have allow you to do. And what we did is to use commercial parts. For example, the mount is from an American company called Plane Wave. We use one of the L mounts they have. They made a small modification for us, but it is a Plane Wave mount. And on the Plane Wave mount, instead of mounting 1 telescope, we mount 4 in this combination. With this is the only ad hoc part we designed to put the telescopes and align them. And we use, as OTAs, we use the Celestron RASA 11 inches telescope. It's an astro camera, used a lot by astrophotographers that produce a very large field of view with very nice quality. And we use a commercial Chinese camera, QHA 600 Pro, that uses a back-illuminated CMOS by Sony, that it is great. It's a camera we also improved before we started working with this design at the observatory. The idea is this module. If we put the 4 telescopes pointing to the same field and combine the images obtained during 30 seconds with the 4 telescope, we can attain the same or a larger magnitude than a 50 centimeter telescope. And this, in fact, it has an equivalent aperture of a 56 centimeter telescope, and provide a little bit more than 7 square degrees of field of view. Remember Atlas, the Atlas units is about 30 square degrees. So if we put 4 of these modules, we can cover at the same time more or less the same field covered by 1 image of the other Atlas telescopes. Advantages, is it not cheaper? Much cheaper. And again, you can buy 1, 2, 3, 4, n modules depending on your funding. Here you have the Celestron RASA 11 design. The field of view is produced at the focal plane is at the top of the telescope, so you have to put a camera in the entrance of the tube. And these cameras, the QHA 600, are almost built for these telescopes. The cylinder has the same size of the optical obturation in the center of the plate where the light enter in the RASA 11s are made more or less for them. As I said, we also tested these cameras before with other old telescope we had in the mountain, and Miguel published a paper with the characteristic of the camera. We found that very nice. They have a more than reasonable quantum efficiency, not as good as they promised, but it's very nice. And with the advantage of having almost zero dead time between exposures. So you can take continuous exposures with the camera. In fact, the dormant time we have in our observations are not due to the cameras, are due to the movement of the telescope when we change field. Right? With basically a very small real noise, so 1.1 electrons, very low dark current at almost ambient temperature, -10. They are cooled with a thermoelectric cooler. So these cameras are very nice and works very, very well, because this is in red, you can see the optimum field of view of the RASA 11, and in blue, you have the chip overplotted within the image circle, the optimized image circle of the RASA 11, and fit very well. So we take advantage of most of the field produced by the telescopes. Sorry. And the other thing that changed respect to the other atlases is that the other atlases use two filters, depending on if the moon is there or not. They use the cyan or orange filters drawn here, together with the quantum efficiency of our cameras. We decided to go to one filter only, because to put a filter change, an automatic filter change in the front of a small telescope is almost impossible. So we have a manual filter changer. We go with one filter and that's it. And we use this filter that cuts at 400 nanometer up to 72,100 angstroms, which is the optimal range for the quantum efficiency of this camera. As I say, we built a prototype. We bought the components, built a prototype, taking advantage of a clamshell that was at the mountain at this moment, that was at the commissioning experiment, the QUEST Qatar experiment. We installed the prototype there. You can see here the 4 telescopes, the mount, and the cameras at the top of the telescopes. And we used it for about a year to validate the design. We shown that the telescope does exactly as we expected, fulfilled all the requirements, and also for the development of the software, the operation and data reduction software. The idea was to install 4 of these modules in an existing roll-off roof dome at the Teide, also from the commission experiment called MAGEC. So we didn't have to build new installations, which is a great advantage. And with these 4 modules, we can cover almost 30 square degrees to the magnitude we want. And in fact, we are building a telescopic installation that has the equivalent aperture of a 1.1 meter telescope. If you think that the telescope built by the IAC is the IAC 80 centimeter, and then the GTC, and then Atlas 1.1, at least in the outlook. 2024, we were able finally to do the job in improving the site, isolating the dome. It was a metallic dome. We put some isolation and internal aluminum cover. We did the pillars for the mounts. We also there was a fixed wall. We changed it in a way that we can open it to allow the telescope that are closer to the west wall to observe without significant vignetting. We built some electricity house with the UPS and so on, and all the domotics for the dome. The dome works alone, open, close, without intervention, human intervention. Mid-January, after a long tendering process, one to forget, the company that got the contract about the planetarium is a sealer in Germany of all these kind of products, came to install and assemble the 4 modules of Atlas 10. It was a very interesting project for them and for us. And you can see here how it looks like the four telescopes look like. Here we have another picture of the 4 modules. And here you have a very nice picture showing not only Atlas, while the IAC wide field telescope. Also, there are the other wide field telescope that is in the mountain, that it is the 1 meter TST by light bridges. So we have now at the mountain 2 wide field survey installations working almost side by side. Pretty pictures of the first light images. And here you can see the telescopes going for flat fielding. This was at the beginning. Actually, the telescope moved all together, thanks to Miguel. But here you can see how the system moves, and at night you can have an image of what happens at night. Then we started the commissioning phase. And during the commissioning phase, and in particular after May that we started the full operations, you can see here how much we did in these 4 months. Here you can see it's something that it is it is the sky observed by Atlas data. You can see the tiles here, because we divided the sky in tiles with the size of the field of view, and this is the tiles we use to plan the observations and so on. We will observe these tiles tonight, etc. And here you can see that at the end of August, some of these fields were observed almost 160 times. So we are ready to have this world map of Atlas data for the next year observations of this region. And for you to have an idea of what we are talking about, during summer we've been observing between 5,000 and 6,000 square degrees 4 times per night, and almost all the nights. Let me say that some of these nights that are in white here are not due to weather, were due to issues with the dome. And this one was test nights using larger exposure times, so we observed smaller fields as a test for the survey. How do we get the images? To arrive to this image, that is the final stacked product of Atlas, we combine the images of the 4 telescopes. Let's concentrate in the central region, right? We have CAM1, CAM2, CAM3, and CAM4 images. And we had to correct these images by flat, and then stack and align and stack all these images to produce the image we have at the bottom. Here we have the process. We are taking every 30 seconds, we take 3 images. So we go to a position, stay there 30 seconds, take 3 images with the 4 telescopes. Then all these images, the 12 images, are dark and flat field corrected and stored in cubes. This is done by our own computer with GPUs. And then there are these data cubes of pre-reduced images goes to a server that do the detection of the stars, the alignment, slightly rotate and shift, and stacking by averaging all the images, producing the final 30-second stacked images with the 12 images obtained with the 4 cameras. And then you can see we can go up to magnitude 20.2, something that we don't see in the individual images. And how it works here at night? What is the night observation? Well, here we have a planning of one daily observing night. The 4 colors are for the 4 modules: Day 1, Day 2, Day 3, and Day 4. And notice that we observe about 700 fields, 4 times per night, plus calibrations. This can't be done by clicking buttons and with an operator there. We need 100% robotic telescope. It has to be done alone in a robotic way. And this is what the project is about. This project, in terms of engineering, is a software project in 80%. And they need to operate alone. Do the planning alone, do the calibrations alone, do the opening and closing alone, execute the observations, reduce the data, and do the analysis. All is done alone by Atlas. How? This is a structure probably more interested for engineers, but let me say that we pick the file sent by the collaboration in the afternoon and say, okay, Atlas Data tonight has to observe these fields. We pick the file, create the observing blocks with a software written by Miguel, and the observing block creates a series of tasks that are stored in this queue. And the master computer of Atlas goes to this reservoir of tasks and pick one and execute it. Pick one and execute it means that it goes there and say, okay, the telescope have to point to this right ascension and declination, store a lot of information in databases, and the cameras, once the telescope is ready, has to do the exposures, right? Let me say that this software is based on what Lightbridge developed for the TTTs. I have to thank a lot Lightbridge people, and thanks for the strong synergy we have. This could be done adapting the software and written in some cases our own parts for Atlas. How it works? Look how Atlas does at night, right? Repeat 4 times the fields, then move, repeat 4 times the fields, then move, repeat 4 times the fields, then move all the night, alone, till covering the whole fields planned to be observed. How we control the telescopes? The telescopes and the focusers are controlled using their own drivers in ASCOM. The ASCOM is a common language for astronomical instruments. And using their driver, we can take advantage of the ASCOM remote server ASCOM remote server software. So for the movement of the telescope, the focusing and so on, we use the drivers that came with the telescopes and this commercial ASCOM software. But for the cameras, we don't. For the cameras, we developed our own software in cooperation with the Lightbridge's people to control the cameras in Linux with Dockers and to take advantage of the fact that the cameras can be read without losing time between images. This is something that the cameras can be controlled via ASCOM also, but the ASCOM driver don't have this possibility. So if you use ASCOM, you have to spend, if you take 10 seconds images, you will lose 3 seconds until you are able to read to expose again. So you can imagine that 30%, almost 30% of the time lost just because of this. Miguel has been working a lot on this stuff, and also with actually the software is very well tested and works fantastic. Again, to illustrate what is going on, we have the telescope, focuser, and mount connected to a Windows computer and controlled by ASCOM. The cameras connected to a Linux computer with GPUs and controlled by our own software that not only take the images, also do the pre-reduction thanks to the GPUs very rapidly, thanks to the GPUs. They are controlled and in communication with the master control system computer that is also one of these matrix computers. And once the images are pre-reduced and the cube produced, the images are sent to the server, and the reduction is done in the server. All this is running on the fly. And few minutes later, after we take the images, the data is completely reduced and analyzed. We also developed thanks to like this and the work done by our team. I will thank Pavel because of his strong work on this kind of control system. We monitor what the telescope are doing at night. We have this kind of monitors that it is based on the TTT monitoring system. That each line is an image, is a field. And when it's done, you have this timeline that it is moving, and you can see if the images is obtained, is reduced, and submitted to the server, and so on. And on the other hand, using the Grafana facility, the Grafana software, we are able to surf in a database, a big database we are producing with all the information of the images, and we can monitor the weather here, the pointing of the telescopes in elevation, azimuth, declination, and right ascension, and our angle. And we have some information on the quality of the image of each individual telescope. Well, before the combination of the final ones, the PSF of the telescopes, the shift and rotation that has to be done to align the images, and so on. This is happening almost online. About 5 or 10 minutes after the observation is done, I have the information here in this monitor and can check if everything is going well or something went wrong. It's all we do. Okay. Notice that the main challenge of all of this is to reduce and analyze on the fly the observations. We need to do it because we are running against other surveys, and we need to do the discoveries and report the discoveries as soon as possible. So to manage this huge amount of data, is a massive amount of data produced by 16 cameras, taking images every 10 seconds, big images of 9 by 6K, we produce about 35,000 images per night that have to be reduced, combined, and analyzed. Implies the intensive use of GPUs and a lot of data storage and so on. That is really a very hard work. There's a lot of work below the funny telescopes. And once the images, those images I showed at the beginning, are finally produced, they are sent to Hawaii. And in Hawaii, they have their own software called MOPS that do the analysis of the image and the search for the asteroid. I can enter in the web page. I can see the other telescopes also, but this is Atlas R17. That is the MPC code of Atlas Teide R17. We can see, okay, this night, the 13th of September, we observed this region, and I can click here and say, oh, show me the asteroids, show me the new ones. And this is what I saw there. You can see tracklets of objects that were not automatically identified by the software. The software has a catalog of orbits of asteroids and comets and spacecraft and satellites and so on, and it's capable of identifying. For example, I can this is one object that in principle the software didn't automatically identify. If I click in review, I go to a page like this with the tracklet, again the image, the subtracted and the detection, one movie showing me the object moving, the plot that I can say, okay, it's a linear trajectory, nice. And it also computes a preliminary orbit and I say, okay, this is 100% a near orbit. Great. But what this does is, okay, I don't have it in my database. I will go to the Minor Planet Center database, check if there is a new one already discovered. And unfortunately, in this case, the object is the first in the list. You can see it very easily, the name here. Can you? Well, it was a known object, but okay, we were able to detect it. Sometimes it says a comet and appear here, or it is a satellite, or the ISS, or the James Webb. I have a lot of images of the James Webb obtained with Atlas. Right? And okay, if it's not an asteroid, if it's not a comet, if it's not the James Webb and so on, but I click and submit it as a new candidate to be a near object. But also, the previous to this one, to do that, the software analyzed it and detected a lot of known asteroids. For example, this night, it detected more than 14,000 asteroids, several of them near asteroids. Measured the position, measured the brightness, and reported these 14 asteroids alone to the Minor Planet Center. It's simply fantastic. What are the results of the commissioning and first observations? Raw numbers up to 17 September 29. Now, today is different. We have observed more than 82,000 different asteroids during these 4 months. 1,288 of them are near objects. We made a total of 372,000 tracklets. So we have 372 by 4 positions and magnitude measured and reported of asteroids. 1,259 of them correspond to near objects. That is the more interesting for us. Atlas Teide already discovered 4 near asteroids, a one Mars crosser object. This is, let me say, is still a little below my expectations, but I'm pretty sure it will improve. But for people interested in supernovae, we reported more than 900 supernova detections with Atlas, supernova candidates. More than 350 of them were Atlas Teide, the first report of the discovery of the supernova. 10% of them have been confirmed with spectroscopic observations. So we are producing a lot of supernova detections with our Atlas. This is an image of a very interesting NEA that we discovered. You can see again the tracklet and so on. We discovered in Nova 30 and the movie of the object. those are the orbits of the first near asteroid we observed at a very different inclination. Some of them passed very, very close to Earth. The close encounters that were very interesting. One of them is potentially hazardous asteroid. Those are very interesting to follow. And the last comment on the observations is our detection efficiency. That is something that related to something that I commented before, that my expectations are not fulfilled again now yet, but it will happen. If we compare, look at this curve. This is the detection efficiency for different magnitudes of near asteroids, right? Based on the real detection done by the telescope, right, in the tracklets. While the efficiency of the telescope in Haleakala is always around 93, 94% for the bright ones, well, those that you don't expect to lose because of well signal to noise for the telescope, you expect to lose for those in the limit. Our telescope is now about 84%. We have to improve. There are several reasons that can explain this. The first one is that we are not using our own wallpaper. We are using the wallpaper produced by the other telescopes with a different plate scale, with a different filter. And this especially works in the galactic plane and crowded fields. Right? We have much more resilience in this region. So I expect this is going to improve. We have to improve also some details on our telescopes regarding to the quality of the images. So, well, we expect to improve this soon and put the Atlas data at the same level of efficiency than the other telescope. Is this expected? Is a new design? Is a new telescope? Is different than to the others? For the others, they have a lot of experience. We are doing the experience with this array of telescopes now. We already published one paper with data obtained with the prototype in 2023. We observed a virtual impactor and get photometry. You can see the object moving in Atlas data images, in Atlas prototype images, and contributed to the characterization of this virtual impactor. There are two papers now with Atlas data submitted. One is the Atlas photometry of the interstellar object 3Y Atlas, and the other is the follow-up of a gravitational wave event, where Atlas put a limit on the initial date of the event. So, where those that do these kind of things can use our data for this study and also the likelihood of a supernova. For the future, we want to implement another method to look for NEAs, that it is particularly good for fast-moving objects, that it is called synthetic tracking. Let me very rapidly explain the basic idea on this. I will not enter in details. Basically, now we talk for images, 30 seconds separated in time. And if you have a moving object and combine images obtained at a different time, you will have, and you are using sidereal tracking, you will have the stars very well aligned, but the asteroid is going to be trailed. But if you do what it's called the track and stack, if you know the movement of the asteroid, you can track, you can shift the images in order to the asteroid stay in the same pixel, and you can have this kind of thing where the stars are trailed and the asteroid is there. Of course, your signal to noise in detection in this case is much, much better. So the idea of the basic idea below synthetic tracking is, okay, we go to a field, we take short exposure, shorter than 30 seconds, so the asteroid is not moving. This is a point-like source in this short, even if it moves very rapidly. And then let's do the following. Let's explore the space of possible movements in terms of vector direction and module of the velocity, do track and stack for the 10,000 different possible movements of an asteroid, and look at the resulting image to see if there are objects like this one. We did this experience with the Atlas prototype, and this is the image. These are 4 images. You should obtain it in the usual way, 30 seconds each. But then we did as a branch of images of 6 seconds to complete the 2 minutes exposure time that we spent here. Here you can see nothing is there. We don't see nothing. But if we use track and stack, the trick here is that we know that there is an asteroid there. We know the velocity is not synthetic tracking, it's only track and stack. But to illustrate what happened is this. We don't see this target, that it is moving very rapidly, 7 degrees per day, and 19.8 magnitude, that it is not present in the tracklets images, not discovered at all. But if you use, and we were able to develop the synthetic tracking technique, we will be able to detect very fine, very rapid moving asteroids, that this is the aim of us, detecting very fast, very rapid in virtual impact trajectory option. So that is something that we can do with CMOS. You can't do with the normal cameras of Atlas, because imagine you want to take a short images, 5-second images with a normal Atlas. Then you have to wait 7 seconds because of the readout time. Then you will be more time reading the CCD than taking images. Make no sense. But with the CMOS camera, we can do something like this. And this is a plan for the future, long future. Well, before going to the conclusions, and as I said at the beginning, for me today is a kind of celebration day. And when you celebrate something, you have to acknowledge all people that collaborate in the success of a project that we're able to build such a system in only 3 years in the observatory. The first of all, I want to acknowledge the support of Rafa Rebollo, the former director. In particular, Rafa was very important during the tendering process in a critical phase. The project survived thanks to his intervention, and I have to recognize his support during the project. Also, I would like to thank the former HUT chief of Telio Observatory, Alex, my friend Alex, that helped me a lot at the beginning. And I also want to ask to thank the administrative support to all the administration people that helped Atlas. Thank you very much. It's hard work. I recognize it, and it's hard for us, believe me. I need to thank a lot the former chief of Telio Observatory Maintenance, Carlos Quintana. He's a key person at the beginning to plan and execute all the prototype and the transformation of the MAGEC site in the Atlas State site. We miss Carlos. And the MOT staff, Miguel and Rafa, they are great. They did a lot of work, and they are always happy to help if something happens in Atlas. They are not here, but I thank them very much. Instrumental maintenance staff, that it is doing now an excellent work upstairs in the mountain, particular to Hector, the boss of the team. They are fundamental for this kind of work. The maintenance people in the observatory and instrumental maintenance are key persons for such an installation like Atlas, such a telescope, IAC telescope like Atlas, work. Without them, we will stop working soon. Also, I want to thank the thoughts that from time to time help me with when some issue happens with the dome or one of the telescopes. Fortunately, it's not very often, but it's good to know that when someone is there, can go there and take some do something. The Teide Observatory contract staff, in particular people that is at night, they helped me at least twice with some dumb issues. They are very nice. I want to thank Antonio Valdes, the Light Bridges CEO, for his disponibility to help a lot since Atlas started to be just an idea. Of course, I want to thank John Tony and Larry Deneau for the confiance and the help, the advices, and so on. It's a pleasure to be part of this wonderful Atlas team. And finally, last but not least, my team. Jose Miguel, thank you for the work you've been done as project manager. Pavel is great. Thank you, Pavel. Always there at night with the kid. After making the kid sleeping, he's always looking at what's going on, and if some problem appear with the computer, Pavel is ready to be there and touch things to make it work. Thank you, Pavel. I will not. I don't have words to talk about Mikel. We started this adventure together in 2019 with all the robotic or semi-robotic telescopes. We learned a lot, and finally his support and friendship was key to come to this end. And the last but the most important key person, I have the great pleasure to work with Miguel, my PhD student, my colleague, my friend. He is unique. I have no word to say how much he worked for Atlas, and I hope you have a great future. In conclusions, this is the first optical robotic telescope, 100% robotic telescope developed and built by the IOC. This is important. Right? This is very important. It's our own telescope. It's our telescope. Right? This is the first EU-funded telescope built and finished for planetary defense. Well, I can summarize several advantages of Atlas Teide. It's cheaper than the other ones. Proved that the array of telescope for wide field images work very well. It's modular, and so it helps the Atlas network to grow. The use of the CMOS camera permit very great different strategies to detect very fast moving targets. The modular design also allow you to use the telescope in different way. We can try to use the 16 telescope together in the same field. It's like to have a 1.1 meter telescope, wide field telescope, to go deeper. And for the observatory, it increases the capability of new research at the Canary Islands, improves the role of the Teide Observatory in the space surveillance awareness programs, European programs, give access to the Spanish community to all the Atlas data product, permit a direct comparison with the next ESA FlyEye telescope, if ever installed. That is something that they need. And also was a great test for a telescope array based on GOTS that is also of the interest of the European community in planetary defense. So I think that that's all. Also, will help us in preparation of ESA mission called NEOMIL, that I am the chairman of the science group, testing and detection with method like synthetic tracking. Thank you very much for your patience, and thanks for.
Thank you very much, Licandro, for a really nice talk. You have given us a wonderful overview of the Atlas 3D telescope and of the whole experiment. So are there any questions in the room?
Very nice talk. Do you process all images every night? Do you process the images every night?
The images are processed automatically every night.
Automatic?
In fact, let me say that I get up early. Now I'm getting up early, I'm swimming. And the first thing I do is to go to the computer and look at the MOBS results. And basically all the data is produced there and analyze it. And I report discoveries or possible discoveries to the Minor Planet Center.
Yeah, but
on the fly. It can be done on the fly. In fact, during the night, someone in Hawaii is taking attention of Teide and South Africa observatories discoveries, and every 3 weeks or so, I take attention in daytime of all the other Atlas discoveries. So a few hours or minutes after the discovery is done, the observation is done, Atlas is reporting any possible discovery.
How do you discover? I mean, you have to do by eye?
Well, no. I explained it during the talk, how the software does it. I can show you. It is basically, I check in this web page. Well, I check in this web page the possible new discoveries. Clicking in the individual tracklets, I go, and here you can see the tracklet, the differential image, the detection, and a movie like the other ones I show you with the point, the object moving. I check if it follow a linear trajectory. I check, because they compute a preliminary orbit, if it is a near asteroid. And I check also if it is a known comet, known asteroid, or a spacecraft or satellite.
Okay, so
only of the few objects that the software didn't detect, didn't recognize automatically as a known. And used to be about 10 or 20 per month, depending on where we are looking.
Okay, so you have to check every day.
No, you have to check only if you have. Imagine that you have 14,000 detections and you have to check them by eye, all of them. That's impossible. The software does it automatically and save those candidates to be a new discovery for you to do the checking, for an astronomer, I, to do the checking and confirm that it is a new discovery, it's not an artifact. There are some artifacts that appear from time to time, and do the final report of the new ones, but only of the new ones. Imagine that in the night we reported more than 14,000 known objects. We also reported about 5 likely unknown targets. Those are the only ones that I look for. It takes me 10 minutes.
Yeah. Okay.
You more questions? Okay, there.
I have many questions. Thanks for the talk, Javier. So regarding the archival of the data, so you said that you produce a huge amount of data. This is archive or remove?
No, we first of all, what we have here is we have all the raw data during 1 week. This is the storage capability we have in the mountain. 3 days. 3 days. Well, we will multiply this by 3 soon. And during about a month, the final products, the stacked images that are much smaller than the raw data, of course, because it's the combination of 12. We store them during 30 days in the observatory, but the final ones, the stacked images, are stored in Hawaii. They have a big database of images there. We don't have the capability. You will need a petabyte or 2 petabytes per year to store it.
So the final combination of all the sky would be somewhere, somehow. So I mean, you're going to have a huge coverage of the whole sky, and with time that is going to be relatively deep. So because you put one of the slides showing the number of frames that you have for the whole sky, and some regions you were getting like 160 or so frames. So this is going to be available forever, or
No?
This is also
This 35,000 images, after
no.
3 days,
I'm not
we
talking
have to
about.
delete.
So show the slide where you saw the number of times that you have been into a given region. It was the whole sky. I think it was before, at the beginning, I think.
This one?
Yeah. So what happened with those tiles?
No, the tiles are all stored in Hawaii.
Okay, so they are in
It's the
principle.
Hawaii database.
Okay. And
But in your case, because I'm thinking in you.
yeah, I'm thinking also in the.
Those images are already flat-fielded, already processed. So I don't know if it can help you
No.
for
This cannot help much, but so and that related to that is so you say this is an IAC telescope, but in fact, so I guess that there's no some nights that you can offer to other groups to do other science, right? So it's fully.
Remember, this is a survey telescope.
Exactly. That,
Even it is an IAC telescope. It is a survey telescope.
exactly. So
To do different programs imply first of all to retire time from the survey,
exactly.
right? And also imply a completely different programmation. Who's gonna do that?
Yeah, I understand. So, but my point is that plan at any horrible future that you can offer a couple of nights to do different science?
No, not in my plans. Maybe someone else.
But we need to push you a bit.
But because of this, it changed everything. One thing is to follow a survey, and the other thing is to do it in a different way.
Okay, and then my final question, which is somehow related to that last one. So you have found that you are detecting a lot of new stuff every night. So and you explore typically to a given magnitude. Do we expect that we will fulfill the discovery space at some point? So let's say after 10 years, all the things that have magnitude 19 or above are discovered, and therefore you can allow us to have the telescope for a few nights?
Not in the near field. Not in the near field. We will continue discovering very small neos coming to Earth. Sorry about. I mean, remember the aim of the telescope, and it is like in any survey, right? There is a basic science driver, and with the data products, other science can be done, like the supernovae, for example. But if we want to say, okay, we will do supernovae this night, we will have to change completely the survey. We will decide to go galaxy by galaxy. I don't know. Or we go to fields where there are galaxies, not where fields they are not by galaxies or whatever. Thinking in this or in other kind of surveys, I don't know. This is the point. This is a survey for planetary defense with subproducts on science that are welcome, and the data is available for all of you, and the possibilities of doing, for example, this started only for astrophysicists, and at a certain point, the UK group come to that and say, okay, we can maintain a copy of your database, and in this database we can run our own software to detect supernova. It's what they are doing. It's a wonderful science, right? But the atlas will not change the survey procedure because of other science.
Well, first of all, congratulations. All the work you have done, it is amazing. So the 4 observations of the same field, I understand you use it for searching your objects, but can we access these individual sources? I mean, these individual images to check like intranight variability of blazars? It is available there?
Yes, stacked images are available for all the community through the Atlas cooperation. Just to do not compete between ourselves, right? There are programs already running that you cannot ask the images to do exactly the same that other Atlas group is doing. We look for interaction and cooperation, not competition between same. But yes, this is available. If you have the capability to transfer and deal with terabytes and terabytes and terabytes.
Well, we can negotiate about that. And the other question is, you can down, I guess the data is now integrated in the light curve that you can get from the web page when you do a request.
Not yet.
Not yet.
It is something that they are working on in the forced photometry.
Exactly.
But on the other hand, something that we would like to do is to integrate our own data reduction, to do our own measurements of positions and photometry, and store in the database we already have with the TTT telescopes. We have a fantastic program for asteroid photometry based on the measurement that TTT does of every object in the fields. They store the results in a database. We search in this database for the asteroids and retrieve all the magnitudes of all the asteroids observed with this telescope. It's something that we would like to do in the future with Atlas images.
Okay, this is exactly what I'm interested on. So on the magnitude, and actually you say you are reducing the data. For instance, gamma ray blazars, we have Fermi monitoring the sky, while Trump is okay to have it there. Let's see. But it takes at least 24 hours. So for fast variability, even if we have a large field of view gamma ray or high energy gamma ray, for Cherenkov telescope, it is too slow. So having in the same night a measurement of the object that see if there is it's going up or down is key for us. And you have it for free in your observation. So it will be great to.
Yes, we have to talk because if in this case, I think that's something that we can discuss within the Atlas team and see how to proceed. The idea is let's go with the proposal and discuss with the Atlas team.
Okay,
how to
thank
do.
you.
Sorry if I missed, but what are the data products, magnitude and proper
The
motion?
data products are basically the stacked images.
No, I mean for the transfer.
One of the data product is force photometry that it is implemented in the Atlas web page, but not still for our Atlas images. You can ask for the photometry of an object in all the database in the Atlas database. They are doing this for supernovae. This is the other data product. The data product on the asteroids is it's a catalog of asteroid positions and brightness, right? Observed by Atlas. As far as I know, this is all the data product.
But you don't have proper motion?
No, we don't measure proper motions.
But that's the.
But
if you don't have the proper motion.
it is not there. It is because there's nobody interested in doing it. If you are interested in measuring proper motion using Atlas data, you have to ask for access to the data and do it yourself.
No, thank you.
Okay, we will not do your science, Arturo.
Okay, I think we have time for one last question.
Yeah, I want to comment on the last discussion on Pepa's. I think that's what she needs. There is a very powerful force photometry server has been running for years, for several years, and you can, I mean, very easily just fill in a web form or by programs. You can look at all the history of photometry of any particular source, point on the sky, not the source, a point on the sky. Since 2015, you can see what is if there is a constant star, for instance, or if there's a transient over there. So you can go. Yeah.
It's the VL. That's why also I wasn't very.
You can write programs to.
Yeah, but that's sources. I know what sources are a lot of regulatory 2,000-3,000 gallery.
Yeah.
Sure.
Okay.
That's why you need to understand how to access the data in a different way. Because now we are part of the Spanish community. So yeah.
Yeah, what the collaboration says, okay, we have a name, we have a limited number of resources. You can have access, but then it's up to you, right? We offer this, but we have no capability to develop more work by ourselves. But if you want,
Just the access to
yeah, the access to.
Okay, well, thank you again, Licandro.
Thank you very much.
And if you have any more questions, you can probably ask him because he's going to be at the ISC for a long time. And the students, please come around and give me your names.
It's well within achieved.
Muy estupenda. Ya me la sabía, pero estupenda.